On the second page, we're looking at logarithmic functions and some properties of logs and exponents. This part 3 problem, we're working with the function f of x equals 1/3 log base 2 of x plus 3. I'm only showing the second page of it here, because the first page had the first part of it was at the very bottom of page 1. The first question is for us to plot 3 points that are on this curve on one of our coordinate axes. To do this, we're just going to use values of x and figure out what the y's are for each one. And I would say that if you want to make your life as easy as possible, since our logarithm is base 2, then picking values of x that are powers of 2 will make life as easy as possible. So for example, when x is 1, the log base 2 of 1 is 0. And so the y-coordinate will be 1/3 log of 1, which is 0, plus 3 equals 3. So on our coordinate axis, we plot the point 1, 3. When x is 2, then the log base 2 of 2 should be 1, so I'll have y equals 1/3 of 1 plus 3, which is 10/3, so 3 1/3. So on our graph, when x is 2, y should be 3 1/3, which is about here. And finally, when x is 4, then y will be 1/3. The log base 2 of 4 is 2. Give myself a little room there. Plus 3. And so that's 3 2/3. So when x is 4, we're up to 3 2/3. So about there. So we can see that this function grows very, very slowly, but that's the case with all logarithmic functions. The domain and range, the easiest thing to know about the domain and range is just to know what the domain and range of log functions are. The regular log function, if I have g of x equal log of x, and it doesn't matter what base the logarithm is, the domain will be everything above 0. You can't take the log of a negative number, and you also cannot take the log of 0. If you're not sure, just ask your calculator, and it will be happy to give you an error. The range of logarithmic functions is all real numbers. So for the general logarithm function, this is the case. There's always a vertical asymptote at the boundary of the domain. So in this case, in the generic case, the vertical asymptote is at x equals 0, and the range is always all the real numbers. So the function that we're given is simply taking the general logarithm, it's scaling the y by a factor of 1/3, and it's adding 3 to the y coordinates. It's not moving the graph at all in the x direction. So these two answers are actually fine for the domain and range of the function that we're given. We should see a vertical asymptote then at the edge of the domain. The logarithm function will always have it'll always have a numerical bound on one end of the domain and then infinity on the other end of the domain. Wherever that bound is on the domain, that's going to be a vertical asymptote in a logarithmic function. So our vertical asymptote for this function is x equals 0 to be consistent with our domain. Average rate of change, of course, is just a formula, so it's f of 8 minus f of 1 divided by 8 minus 1. As we talked about before, that's the average rate of change of a function from 1 to 8, and then I just have to evaluate the function at those two numbers. I already evaluated the function at 1. Remember, I said that f of 1 was 3 earlier, so that one I've already done. And if I evaluate f of 8, I'll find out that f of 8 is 4. So I have 4 minus 3 over 8 minus 1, which is 1/7. So the average rate of change of this function from 1 to 8 is 1/7, and that sort of accounts for why we see such a slow growth. That means that if I were to look at the graph starting at x equals 1 and ending at x equals 8, the graph entirely has grown by 1 unit. So it's taken it 7 units to the right in order to go up 1 unit across that interval. The last question is to sketch, I guess it's not the last question, the next to the last question is to sketch a picture of the inverse based on, I guess I never did draw the function, did I? So the function itself has an asymptote at 0, x equals 0, and it's got to go through these points, and so it's going to hug the y-axis going down. It's got to go through those points going over, and you can see that it does have an x-intercept very close to 0, but we never did figure out what that was. That's actually a good question. You might want to ask yourself, what is the x-intercept for this picture, and see if you can answer it. It ought to be someplace really close to 0. When I'm talking about f inverse, the main thing I want you to know is that the graph of f inverse, you're using the same points that you graphed on f, but the inputs and outputs have been reversed. So the x and y coordinates should be flipped for the points that we plotted. So remember, we plotted the point 1, 3 for the graph of f. So this was the point 1, 3. That means that on the graph of the inverse, I should go through the point 3, 1. This point was 2, 10/3, and so on my other graph I should have 10/3, 2. So 10/3 is a little more than 3, 2. And then finally, the last point I plotted before here had an x-coordinate of 4 and a y-coordinate of, what do we say it was, 11/3. So 11/3 is also quite close in here, but we're up to 4. So again, just flipping the coordinates, this point has coordinates 11/3, 4. And so we can get a general sense for the shape. Remember that everything is being flipped. So before, where we had a vertical asymptote at x equals 0, in the reverse graph I'll have a horizontal asymptote at y equals 0. So what I should see is a graph that is hugging this axis and then comes up like that. So this will be the mirror image of the other graph. To check that, or to make sure that that's right, we can actually find the algebraic rule for f inverse of x by going through the process that we use for algebraic inverses. Namely, take our equation written in the y equal form, so that was y equal 1/3 log 2 of x plus 3. Remember, we started with that. We switched the x and the y. So I rewrite this as and that's exactly doing what we did with the coordinates. Remember, when I just drew those coordinates, I switched the x and y coordinates. So all we're doing here is saying, in this equation, I'll just switch the role of the x and the y. This now is a correct equation for that describes the graph of f inverse. But to get the rule for f inverse of x, I need to solve this equation for y. I need this to be in the form y equals something. And so the rest is going to be algebra trying to get at the y. And this will be the same algebra we've done several times. So the first thing I want to do is get the log of y by itself on one side, which I can do, and I'll compress 2 steps here so that I can save room. I'm going to subtract 3 from both sides, and then I'm going to multiply both sides by 3. If I do that, then on the left side I'll have 3x minus 9, and on the right side I'll have log base 2 of y. And I know that once I have an equation that looks like the log of one thing equals the other, I can just swap this for an exponential expression with the same base. The logarithm is base 2, so my exponent's base 2. But now, instead of y being the input into the logarithm, y is going to be the output of this, and instead of 3x minus 9 being the output of the logarithm, 3x minus 9 is going to be the input for my exponential expression. So the formula 2 to the 3x minus 9 power is my formula for f inverse of x. And if you wanted to check, you could ask your calculator to draw a picture of that and compare it to the graph that we sketched by just doing the symmetry from the original picture, and they should match up.